Well, welcome back, everyone, to ASFPM Annual Conference. This is session B3, and we have three presentations for you today. My name is Steve Boning. I'm president of Coastal Waterways Engineering here in sunny Florida. And good afternoon to most of you, perhaps good morning to the rest. We're going to get started right away. We have with us today from CDM Smith, Brian Caufield, and his presentation is Conveying the Various Messages Around Coastal Erosion.
Good afternoon. Today I'm going to be talking to you about the various messages associated with coastal erosion. Background behind this presentation is that we know that coastal erosion is a hazard to lives, property, and resources along U.S. coastlines. Federal and state agencies are developing information and providing it to users for mitigation actions or planning actions. And so the plan of this discussion today is to talk about the various information out there and how we can use that. The U.S. Climate Resilience Toolkit has information related to the loss of $500 million.
Coastal construction manual
of coastal property losses associated to damages to structures as well as land loss. The federal government is spending about $150 million per year on coastal erosion control and beach nourishment, and 80,000 acres of coastal wetlands are lost annually. There's two types of erosion. The first is episodic, and that's the response of the beach to an individual storm event. What happens is the sand is moved usually from the upland areas that are impacted by storm offshore into bars, and those bars then weld back to the beach in quiescent times. And then there's a response of the beach to long-term processes such as changes in water levels, so respect to sea level rise, changes in wave climate, or even changes in the amount of available sediment. FEMA is one of the federal agencies that does provide information with respect to coastal erosion. It's done through the Coastal Flood Hazard Analysis. 44 CFR 59(2) states that communities participating in the National Flood Insurance Program must have adopted floodplain management ordinances that account for flood-related erosion damages. That's performed through when we delineate the coastal high hazard areas, or the VE zones, we map the 1% chance wave crest elevation, and we account for the erosion associated with that storm event. So how is that done? Prior to the mid-1980s, the assumption was that dunes did not provide a barrier to coastal floods, but we knew that wasn't necessarily true. So a series of studies were performed in the late 1980s, and what they looked at was how dune volume changed in response to individual storm events. A total of 30 storms had collected, or during those 30 storms, there had been a collection of beach and dune profile change. So the dune volume change was collected, and the median value was plotted against the return interval of the still water level of that storm event. And so if you were to go out on this graph to the 100-year event, up to the best fit line and across, you discover that you have 540 cubic feet per foot, or 540 square feet, which is what we all commonly refer to as the 540 rule. The FEMA Coastal Construction Manual also provides information with respect to coastal erosion. The recommendation is, of course, to consider the erosion that occurs as part of the flood insurance study, considering the dune and bluff erosion, as well as any long-term erosion when you're siting your structure on your property. What's interesting, though, is they don't recommend using the 540 square foot rule to evaluate the protection provided by the primary frontal dune, but instead to use a value of 1,100 square feet. And there's three reasons behind that recommendation. First is the fact that the flood insurance studies are done at some point in time, and it's not known when that map or the profile analysis had been performed in comparison to when you're trying to site your structure. So there could have been some long-term erosion that has occurred. Additionally, there may have been two storm events that have occurred in short impact to one another with varying magnitudes, and the dune has not been allowed to recover. Also, as I mentioned, it's the median value of dune erosion that's been mapped are being analyzed, and therefore you're underestimating erosion 50% of the time with that 540 square feet. The U.S. Army Corps of Engineers is another federal agency that is involved in coastal erosion. After Hurricane Sandy, they got experts together to evaluate what damages occur to a structure based on the percentage of the footprint that's been compromised by coastal erosion. And so the graph here is representative of a single-story dwelling with a basement. And if you were to go to that full report, you'd be able to find multiple series of curves for various structure types with basements, without basements, multi-stories, residential, and non-residential. The Corps of Engineers also, of course, are participate in development of coastal erosion modeling tools. They've evaluated cross-shore beach profile change with models such as S-Beach or Seashore. And then they look at longshore profile change with models such as Genesis, N-Line, and the newer model of the coastal modeling system. There are other tools out there, of course, being developed by proprietary software firms as well as academia. The U.S. Geological Survey is also involved in coastal erosion. They actually have their Coastal Change Hazards portal. This happens to be the landing page. What you see is information available is the events of 2020, so the various hurricanes that occurred. They also can provide information for extreme storms. They provide information related to shoreline change and finally sea level rise. I'm going to look at all of those except sea level rise. But what are they looking at? They're looking at collision, overwash, and inundation. So collision is when the water level is high enough that it impacts the dune itself. So you're going to see dune erosion. Overwash is when the wave crest elevation is higher than the dune crest elevation, and therefore waves will overwash the dune. And finally, you have inundation, which is when the storm surge elevation is higher than the dune elevation, and you inundate the entire profile. So when they look at these model results or their forecast results, it's provided in probabilities of these three events. So let's look at one of the events. This happens to be Hurricane Zeta, which was the end of October of 2020. And the area I'm looking at in this example is Dauphin Island, Alabama, which is one of the barrier islands in the Gulf of Mexico. And what you see going from onshore to offshore are those three probabilities represented as colors, with red being 75 to 90% chance of impact. So you can see that collision is expected, highly likely to happen along all that length of shoreline. There is a changing chance of overwash and then an even lower probability of inundation happening. So how well was this forecasted? Well, here's a picture from the NOAA emergency response imagery flown after Hurricane Zeta. And you can see that the dunes were impacted. That's based on you can kind of tell from what color of the sand and what's happened on the non-populated area of the island. And then on the right-hand side, you can see that there is some overwash. You can see some how sand has moved back from from where the structures sit, but you really don't see evidence of inundation. For extreme storms, they're doing synthetic events, looking at hurricanes and nor'easters. For the hurricanes, they're using the model results of water levels from the SLOSH model, and then they evaluate the waves based on the wind speeds of those 5 different categories. And for nor'easters, they provide information for the 3 classes of nor'easters, again, getting the model results from the extratropical model and using the wave heights associated with the wind speeds of those 3 classes. They provide information related to shoreline change, looking at long-term and short-term. The long-term are 78 plus years and short-term are 30 years. You really want to use the long-term when you're doing planning projects. The longer the time span, the more shorelines you probably have in there, and you're better able to represent the physics of change. In short term, there might be individual projects that might be impacting the actual analysis. This area that's being represented is Chatham, Massachusetts, which is Outer Cape Cod. It's where the sharks like to congregate in the summer. You can see on the southern Monomoy Island, the short-term erosion shows it being accretional, which is true. That's where all of the seals are liking to sit out right now. And you can see that it's erosional at the inlet mouth, and a lot of that is because of new inlets that have opened in the last 20 years. But in the long term, some of that part of the shoreline is being shown as accretional, and that's just because of the fact that the spit has been growing through time, and that those inlet dynamics are part of how that spit opens and closes. All this information is coming from historical shorelines. This is all downloadable information through the Coastal Hazard Chains portal. What you do see here, though, is that those last figures showed coastal erosion as part of the barrier beach systems and not within the bays. So the bay that's right immediately behind the barrier beaches, which is Pleasant Bay, and then you can see the developed portions of Chatham, and then the south side, south-facing shoreline, which is Nantucket Sound. And there are shorelines available there. And so state agencies, such as Massachusetts CZM, leverage those shorelines in their own coastal erosion hazard analysis and provides that information to homeowners and community officials through ArcGIS online information. Other states also provide information related to coastal erosion, whether they be static maps or erosion rates at certain transects. And those are usually, again, provided through coastal zone management agencies of each of those individual states. USGS has also developed an experimental product called the Total Water Level and Change Forecast Viewer. This is inclusive of tide, surge, and wave runup. They're coordinating with NOAA and the National Weather Service to obtain information from the operational forecasts of the water levels and the operational forecasts of the offshore wave conditions. Those are then combined into a wave run-up model that's an equation from 2006, and they're using beach slopes based on airborne LiDAR surveys. This information is provided in a different way than how they provide it in the Coastal Chains Hazards portal. It's provided in a more graphical sense as part of a forecast. So this is a landing page for that total water level and change forecast viewers. You can see that it's not 100% coverage across the United States. It's through most of their the National Weather Service forecast offices. And if you were to select one of those radio buttons, you'll be able to zoom in as to what's available. So of course, I've selected the Boston Weather Office. When you land, it shows you the most recent forecast. You have the ability to select a forecast date. You can get single site details or regional overview. And as I mentioned, you don't gain 100% coverage. You can see that there's a few areas of the shoreline that aren't part of this model. You can see that portions of the inner Cape Cod Bay are not available. And as this is a most recent forecast, and it's a quiet time right now, the dune impacts are mostly unlikely throughout this entire area. They also, again, provide that potential dune erosion, which, as used in their other system, is collision. There's overwash and inundation. So we're sticking with some similar nomenclature with some differences. So I want to show you an example forecast. This is February 2nd, 2021. I've selected a single site, which is Scituate, Massachusetts. And normally, if you go to the website, the model will play and you can see how the time varies. The color of the beach profile will change as well. Right now, you can see that color is showing as potential overwash. As I've stopped it as the peak of the event, the dashed line represents the water level, the solid line represents the wave run-up elevation, and then there's a light blue around it, and that's partly respect to the fact that there is errors associated, plus the water levels kind of vary through time. So there's, but you can see that it's showing potential overwash as part of this event. Underneath the image on the left, you can see that this event, there was potential inundation at one site, overwash at almost 100 sites, and collision at 200 sites. So again, thinking, how well did this forecast do? Well, it did pretty well. So this is a screen capture of a drone video posted to the WX Chasing Facebook page. Also, this is a great individual to follow on Twitter at bclems. He does a lot of drone capture post storms, whether they're hurricanes or nor'easters. And what you see from this screen capture is the fact that we're definitely seeing overwash. We're seeing wave spray up against the houses, and you can see water pooling on the upland side. So again, this experimental operational model is doing a pretty good job of indicating the true impacts locally. Another newer product coming out is the Technical Mapping Advisory Council made recommendations to FEMA to account for coastal erosion with future conditions and sea level rise. So FEMA Region 1 has done a test pilot study on that, looking at, since FY17, developing coastal erosion hazard areas throughout the states of New England. The idea is to leverage these existing shorelines from the USGS or state developed shorelines, looking at sandy beaches, coastal bluffs, and even ledge, applying a sea level rise accelerator term to long-term erosion rate. And that's the idea that long-term erosion, the observations of long-term erosion have observed the sea level rise up to this point. And so we can forecast then how the erosion rate goes in the future based on the expected sea level rise. We also assume that these natural protected features erode back along a nearshore beach slope. So kind of just basically will move back in time at a slope comparable to the current time period. The maps are developed and polygons are made of the coastal erosion hazard areas. This is an example image of the paper map for South Shore of Nantucket Island near the airport. The yellow line represents the 2030 scenario, the red line represents the 2050 scenario, and the purple line represents 2100. And this is for the intermediate high scenario at this location. There's a total of 4 mapped sea level rise scenarios that are made, and all these polygons are provided to community officials via a FEMA ArcGIS online server. So you can just go to that website and you can actually surf the available information. As of right now, only Nantucket, Dukes, which is Martha's Vineyard, and Barnstable, which is Cape Cod counties, are available, and more counties will be posted as the study progresses. Some interesting information related to coastal erosion that you can help with right now is citizen science for grain size. This is a program called SandSnap, which is a coordination between the U.S. Army Corps of Engineers, James Madison University, MARTA Science, and the USGS. So the idea is we don't know grain sizes on many of the beaches of the United States. We really only get that information in areas where we've been doing coastal studies. And so you can help when you go to the beach this summer. Go to a dry portion of the beach, scrape down about ½ an inch so you can expose the sand that's underneath the windblown sand. Hopefully you've got a US coin in your pocket. You set it down, you take a picture with your cell phone, and then you come back home, you post that picture to ArcGIS online site developed by the Corps of Engineers. So you go to this, if you just search for SandSnap on the web, you will find this this web link, and you can get there and just upload your photo. Another product that's out there right now is, and again, citizen science for beaches though, so this is beach change. It's called CoastSnap. So go to coastsnap.org. And if you happen to be out on a beach this summer and you see one of these trays that have CoastSnap on it, you just set your camera in the tray and you take a picture. And the tray that's being represented is Sandwich Town Neck Beach. So that's Sandwich, Massachusetts. They've got an east facing and a west facing tray, and you take pictures in both directions. And knowing the time and location of the pictures, you can then create movies of these photos so you can see beach changes through time. And it's truly a global citizen science going on. You can see from the image on the right-hand side that many beaches in many areas currently have these CoastSnap trays in place. So are there any questions?
Steve, I think you're muted.
I am muted. That's terrible. I'm so sorry. Welcome, everyone, back to, and thank you, Brian. We do have Brian on here to answer questions. And again, I should have reminded everybody that you can answer your questions, or ask questions rather, during the presentation. So feel free over the next couple of presentations to do just that. We have a question here I'm going to go ahead and take is question number one is FEMA accounting for the impacts of groundwater flooding in low elevation coastal environment. And the example given is Miami. What about compound flooding events?
Yeah, so I mean, that's one of the aspects of flooding that we're not really looking at right now. It is an area, if you kind of remember from the lunch presentation that Nicole LaBeouf discussed, Noah looking at some compound discussions in that water model. But the groundwater is still one of the components that we are kind of not including as we look at any of our analyses. It's just not in there. We tend to look more at the joint probability of riverine and coastal flooding, but not getting into that, the groundwater high tables and the impacts on coastal floods.
Okay, we have a second question. For riverbed erosion, you can use Exner equation. In the case that you presented, what kind of model do you use to estimate the long-term shoreline change, say on the order of 78 years plus?
So for the long-term erosion, we're actually not doing any type of modeling at this point in time. The long-term erosion is solely based on observations. So it's taking aerial photographs, it's taking those T-sheets from the 1800s, and with that information, you identify. It's a little bit tougher in the the coastal realm because you have to figure out what tide is happening in the imagery, because you're then trying to map basically essentially mean high water, and so that of course can be in a different space in those aerial photographs. And luckily now we're moving to LiDAR data sets, so you're just able to extract say 0 NGVD 1988, or you can choose whatever the local mean high water elevation is relative to that datum, and then you combine where that location is set to some reference line, and then you measure the distance to that point, and then you take those distances, you plot them on a graph, and then you do a best fit line through it. And it's kind of some methodologies that have been implemented by the USGS. They've developed tools. The last ones I used were in MATLAB, but I'm sure they're in R and Python by now as well. And so it just does a linear fit through all of the data points through time to come up with the erosion rate.
Okay. Got another question. This one, actually, Brian, you and I had a little discussion earlier about your presentation, and you did mention a project you were working on with regard to sea level rise. This question is, do you anticipate FEMA regulating future coastal development based on projected sea level rise models?
I think through time, I mean, the program is going to have to adjust as we all heard during the opening plenary from David Morstad, climate change is going to be one of the components moving forward based on the Biden administration. And it's, how does that get incorporated? As I kind of mentioned, that was guidance also provided by the Technical Mapping Advisory Council after Biggert Waters. How do we account for these future changes? I think that right now that my expectation is that as sea level rises, we'll continue to be going back into certain coastal communities and making updates to coastal flood hazards. I don't know at this point in time if we're going to be kind of including from a regulatory standpoint, if we were to add, some future condition sea level value and then add that to, our points. I don't know if we're headed that way yet, but I could definitely see it in these non-regulatory products, such as the project that we're doing in FEMA Region 1.
All right, great, thank you. Another question, how does the USGS predictive modeling take into account wave run-up? Do they have detailed coastal topography for this modeling?
So they don't have, it's not detailed, they're doing it on almost like a kilometer spacing. So it's a fairly wide spacing. They are taking LiDAR data sets and they're coming up with an average beach slope. And so there's an entire report methodology that USGS has put out on that of how do you obtain these average beach slopes from the LiDAR data sets. And then they're using Hillary Stockton's model, which is a 2006 paper. And it's just a simple empirical equation where you can use it to solve for wave run up, and it's inclusive of wave setup and other factors. So it's not detailed in the sense of, it's a LiDAR transect that's been cut. It's more of an aggregation of an average slope over an area, and then the equations being applied with those input conditions.
Another question, can you elaborate again why the dune erosion criteria needs to be updated from the 540 square foot rule to the 1100 square foot rule, which is close to the rule for the 500-year event?
So the 540 rule stays in place for FEMA's coastal flood hazard analysis. So whenever we're doing a transect-based analysis, for flood insurance rate maps, we go with that 540 rule. But the coastal construction manual, it's not that it's using the 1100 square foot as a rule. It just makes as a recommendation that if you want to evaluate the primary frontal dune at your project site, so like if you're building a home, behind the dunes and you're siting it, and you want to properly account for, is the dune in front of me going to be protecting us? Then you want to look at it at that volume and look at it not from a 540 sense, but from the 1100 sense. And the reasons behind that are those threefold rule issues. The first is you don't know when that map was made. So how long ago does that map actually measure the volume? And if there's been long-term erosion, then the dune has probably been eroding through time. Also, the 540 rule is based on a median value for the primary frontal dune volume. And so we're kind of underestimating dune erosion about 50% of the time. And then the third issue is just with respect to if you have two events in short order, the dune volume has not been able to recover. And so the dune may be in a non-recovered state, so there's not enough volume in there. And so there, the kind of the recommendations in the construction manual is to look at it with a larger dune volume versus the 540 value.
Okay, and I think we have time for one more, and this might be a little bit of a segue on the last one. Could you see this work being used to make some regulatory decisions, such as instilling setbacks from water bodies that cause chronic coastal erosion?
So there are, I left some of those discussions out of the presentation, but for those from the state of Florida, you're familiar with the coastal control line, and that's a setback line. It's not based on an erosion, approach, but it's kind of one of the factors as to why they have those types of control lines. It's, if you're going to build inside of that control line, they want you to be building to certain standards, and if you're outside of the control line, then using different standards. So I feel like there's a lot of agencies out there already, that have these recommendations for regulatory guidance. If you were to build in a VE zone, the guidance is that and that's accounting for dune erosion. You need to build on a open pier or pile supported foundation. You can't have only storage beneath, right? You got to build to the lowest horizontal member being above the base flood elevation, and then local communities also have freeboard requirements. So there's a lot of kind of examples of how there already are regulatory components included with evaluating erosion and its potential impact on project sites.
Okay, fantastic. Thank you very much, Brian. Brian Caufield of CDM Smith. We really appreciate you joining us today and presenting.
Thank you.
All right, we're going to move right along to our next presentation. This is called Extreme Storm Event Preparedness, GIS Mapping of NCDOT's Vulnerable Bridges. And we have Brian Ratakovic from NCDOT that will be presenting for us.
Hi there, my name's Brian Ratakovic with NCDOT. I'm here to talk about GIS mapping of NCDOT's vulnerable bridges. Along with me is Matt Lauffer, who will be here at the end of the presentation to help answer any questions. So a little history and background. This impressive image from NOAA depicts the paths of all major hurricanes and tropical storms affecting the U.S. over the last 150 years. So we get in a little bit closer to North Carolina here, and this shows all of the named hurricanes that have hit or have just been off the coast of North Carolina from 1851 to 2020. From this data, we can see that we've had about 84 storms make direct landfall. 300 have affected us within 150 miles for a total of 387. 85 of those 380 storms were a Category 3 or higher. And North Carolina experiences a direct landfall major hurricane event on a 5 to 7 year return interval. So a Category 3 or greater storm made direct landfall with North Carolina about 23 times in that time period. So in 2004 and 2005, Hurricanes Ivan and Rita, caused significant damage to critical bridges. So the FHWA initiated a pool fund contract for the development of specifications for bridges vulnerable to coastal storms. 10 states were involved in the pooled fund study, and North Carolina was one of those states. So AASHTO published their guide in 2008. One of the teams on the research was Ocean Engineering Associates. NCOD contracted with OEA in 2020 to study our coastal bridges for vulnerability to storm surge and wave loading. So the objectives of the study were twofold. One was to establish, 100-year design conditions for North Carolina coastal waters and to present the results in a surge wave GIS database. And from that surge wave data and bridge information, identify bridges vulnerable to this type of loading. A bridge was considered to be vulnerable if the surge wave forces and moments exceed the resistive forces and moments created by the dead weight of the superstructure for any of the spans. And a level 3 storm surge wave analysis was performed to provide the design water level and wave parameters needed to compute the loads. So the storm surge and wave modeling, we received data from Ocean Weather, a firm out of Connecticut. And basically OEA used ADCIRC and SWAN to model the storm surge and wave modeling. ADCIRC is a numerical model developed specifically for generating long duration hydrodynamic circulation along shelves, coasts, within estuaries. SWAN is a numerical model for estimating wave parameters in coastal areas, lakes, and estuaries. Both models use element mesh that has over 200,000 nodes. So the number of nodes is governed by the required accuracy that we want. The more nodes we have, usually can increase the run times and makes it not as efficient as it needs to be. So the mesh was configured through the application of an algorithm that relates the mesh elements size to both the local bed and local bed gradients. The mesh was then modified to increase the resolution in the regions within and surrounding the coast of North Carolina. Once generated, mesh nodes are assigned elevations using topography and bathymetry interpolated from NOAA data sets. So once the models, were created, they had to be calibrated. So they used 3 types of data: water surface elevation, hurricane high water marks, and wave data. They had to make sure that the parameters of the water surface elevations matched within acceptable limits using FEMA criteria. And as you can see here, there's a little bit of detail of the ADCIRC and observed for Hurricane Isabella, Floyd, Fran, and Bonnie. And they came pretty close. So this is how the simulation kind of proceeded. A hindcast procedure employs the tightly coupled ADCIRC and SWAN model. So basically, the models share an identical mesh. They pass wind speeds and water levels, currents, and radiation stresses, efficiently allowing them to run sequentially in time. The procedure begins with the application of the storm surge model, ADCIRC. So ADCIRC simulates the conditions and then passes the information to SWAN. SWAN simulates simulates wave generation, transformation, and braking for a set amount of time. Then SWAN passes that information back to ADCIRC, and ADCIRC will calculate the water surface elevations and currents with the radiation stresses as an additional input. This process continues for the duration of the hindcast. So we had to choose, we examined all historical tropical storms and hurricanes occurring within 100 miles of North Carolina. 62 storms were selected in a 160 years period. And for an additional data, we basically shifted the storm's path by half a degree, about 30 nautical miles left and right. So with those additional simulations, we had an effective of basically 480 years worth of data. And this here is just a visual showing which storms we chose, again, starting from 1857 all the way up to 2007. The hindcast produces wind speeds and directions, water elevation, depth, average current speeds and direction, significant wave height, and wave peak periods at each grid node for each time step throughout the storm. We also had an extreme value analysis done. This provides a method to estimate different return interval values for the quantities produced by the tropical storm and hurricane hindcast. The details of that can be found in Appendix E of the report. But for example, the 100-year return interval value, water surface elevation at a particular bridge location can be estimated from the results of the simulations of past hurricanes that have impacted that location. So the EVA produced two sets of data, the 100-year water surface elevation and the associated wave height, and the max wave height and the associated water surface elevation. These data is needed to compute design wave forces and moments for the subject bridges. Just note that the max wave height does not necessarily occur at the same time as the max 100-year water surface elevation during a storm. Also, these do not account for sea level rise. At the time, it was not recommended for consideration when they were developing this report. So the wave loading and bridge vulnerability assessment was done by OEA. They basically had some predictive equations developed by Dr. Max Shepard and the graduate students of the University of Florida. Basically, they determined a vulnerable bridge is one where the surge wave forces or moments exceed the resistive forces and moments based solely on the span dead weights on one or more spans. So the results from that, we saw that we had 105 bridges that were vulnerable to the 100-year surge wave. NCOD reviewed the 105 bridges and identified 61 of these to be further studied. Now, as you can see here, this is a sample output of the information that was given to us. It has the information for each of the spans, 100-year water surface elevation, span lengths, a lot of information in here. Also provided was a profile. So for each of the So NCOD published a report in 2013. The results presented in the final report and an accompanying database. So in 2015, also, we added the 5, 10, 25, and 50-year return interval data. So the GIS database provided to us, we had 61 bridges selected for the detailed analysis. And for each item, for everywhere, the GIS database basically provides the depth average current speed, the current direction, wind speed, water surface elevation, wave crest elevation, and significant wave heights for the 5, 10, 25, 50, 100-year return interval, and the maximum values for 62 storms. So the data is presented into a GIS database. As you can see here, we can go on and select and turn on different levels, different layers based on the storm return interval and what data set we want to see. So we have information for the, the 100-year water surface elevation, the depth average current speed, the 100-year current direction, the wave crest elevation, and significant wave height in feet. And as with every GIS map, you can change the background if you wish. So with that data, we contracted the engineering firm Wood to create an AGL map that includes data for the 61 analyzed bridges. This GIS web allocation was developed to provide a convenient way to access and display the data from the Superstructure Level 3 Wave Vulnerability Study final report. So we're going to kind of just go through it a little bit here. So, you know, again, you can change your base map to whatever pleases you. On here, the map, we can share it, which was kind of nice. So if you're zoomed in at a certain view, you can share that specific view. You can do different searches based on span vulnerability, or if you happen to know the span number. I usually do span searches by the bridge. So once you type in a bridge ID, you apply, it'll take you to the bridge. And as you can see here, we have all the information. The PDF file is the report that was produced that is inside that has the list of all the information. It's kind of a lot in here, so I think that's kind of lends itself to why we created the GIS map. So it's a lot easier just to click on here and go to the you know, the 10-year hydraulic data and pick a specific span that we're interested in. And then we can see, you know, what the significant wave heights are and the wave crest elevations for that span. You know, you can also zoom in and pick other bridges. We'll go in here and you can see we have all the different spans are labeled. So all the information's right in here, along with, you know, name of the road and some other information. We can see the report if we want to, and we can get into the actual data. So if we want to go see the 100-year water surface or the 50-year hydraulic data, change it to span ID. So if we want to see, you know, for span 145, scroll down, and there it is. So there's the data that's for that span. And then you can select other spans and view them that way also. One more thing I want to talk about is that we can also change, we can add certain layers. So we have the ability to turn on the weather radar, storm tracks that are part of this. We can also display all the bridges that were in the study that maybe were not analyzed, just for a reference. And we can even include, you know, all DOT bridges just for fun. So, you know, that's the map, that's the data and the GIS. But how are we using this data? So first of all, we're using it for analysis. The return intervals on hydraulic design reports. We're using it to analyze existing bridge and locations for new bridges. We're using it to determine vulnerable coastal bridges during tropical storms and for bridge watch alerts. So, you know, we use the data in our hydraulic reports to help us complete the information that has to be shown on plans. We use data to provide water surface elevations for reported return intervals. For scour analysis, you know, the parameters needed for bridge scour evaluations can be derived from this study as well. For less critical routine coastal bridge replacement projects, using data from this level 3 study can save the cost of having to do individual 2D models and provide a more reliable science-based approach than the simplified storm surge estimation method that we have used in the past. You know, structures management unit uses this data for analyzing existing bridges and locations for new bridges. So the GIS database is large and has not been made publicly available. So basically the hydraulic staff provides the data in a tabular format for specific locations on the request. So, when you get a design for a new bridge, they provide us usually the location of the new bridge, and then we'll come through here and in the GIS database, gather the data that they need. So, it's for a long bridge, so it takes a lot to pull all that data out. This is an example of data that we'll provide to them for long bridges. It's a very tedious effort to populate these tables for us. Our goal is to hopefully get those contour level data on the AGOL map, so it can be done publicly and by lots of people. So before we get into storm surge and how we use it to help protect the vulnerable bridges, I just want to say we get our information using SARA, Coastal Emergency Risk Assessment, to obtain the tropical storm surge data for analysis. The SARA web mapper is pretty user-friendly and visually appealing. They basically use AdCirc model, which we'll get into in a second here. So, hurricane forecasts typically focus on a storm's track and maximum wind speeds. SARA uses AdCirc, a deterministic approach computer model with a 25-year track record of success to calculate the storm surge corresponding to the latest official hurricane forecast track. The AdCirc storm surge model is a hydrodynamic simulation model developed for the purpose of predicting flooding impacts from ongoing and potential future storm events. It's a very sophisticated model. During tropical storm events, model guidance is computed by the Texas Advanced Computing Center, the Louisiana State University, and the Renaissance Computing Institute from the University of North Carolina. So in a major storm event such as Hurricane Dorian in 2019, NCDOT used the data from the SARA website to obtain storm surge data predictions on the event. This was then put into the GIS web application to easily see which coastal bridges were in the predicted storm track and to quickly assess whether any of these could potentially be vulnerable to damage from the approaching storm. Just going to kind of step through it here real quick. So during a storm event, we would have our firms go ahead and load up the storm tracks from SARA, and we can turn them on in here. So this was storm track 48 from Dorian. And as you can see now that it highlights all of the bridges that have spans below water. So we can zoom in on some here. And the data presented will give us how much inundated it is. So this one's about 2 feet, that span. Also provided in the forecast, we have the max water elevation and the wave elevation also. So we can go back and get some information about how high the waves are going to be and how inundated the project is. Now, this is pretty useful, but sometimes you need to transfer this data to other entities, other stakeholders. So Wood created this nice little tool for us that basically we can decide to input all the effective bridges and spans for either a division or the whole state. So if we do it for the whole state here, you can see that about 245 spans are affected, and it has information for each of those spans listed out. What we can do with that data is view it in different ways. So if we want, we can go ahead and view it as a CSV file. We can view it as an attribute table at the bottom if we're looking just for one thing specifically. We can export it to a mapping feature. I work with Excel a lot, so I like to place it in Excel. As you can see here, once we get it in Excel, you can do some pivot tables and you can find out exactly which bridges are affected and how inundated they are. So these are inundation depths over the bridge for Dorian for that track. Data can also be imported into other AGL maps to help us compare vulnerable spans with various other data points, such as evacuation routes and evacuation orders. This map here displays all the evacuation routes in North Carolina, along as evacuation orders for Dorian at that time period. The bigger the circle, the higher the inundation depth. So probably any big circle that's on an evacuation route, we'd want to check out and let our emergency personnel know. Another thing is BridgeWatch. So BridgeWatch is a real-time web-based bridge monitoring software application developed by US Engineering Solutions. And it helps bridge owners like ourselves. It provides us an early warning system for bridges that may be affected by flooding. BridgeWatch collects data from different sources such as NOAA, USGS, our own North Carolina emergency management gauges that are out there, and it compares those data, that real-time data, to thresholds that we have set, and we get an alert whenever a threshold is exceeded. Coastal bridges in the system have thresholds based on the lowest low steel elevation data collected from the wave vulnerability report. When a slosh threshold exceeds those elevations, an alert is sent out to us. This was a Hurricane Dorian, or I'm sorry, Hurricane Zeta from 2020. We got an alert because the threshold for this was just a foot. So this tells us that, you know, maybe we should take a closer look at it inside the AGOL application. So I want to say thank you. You can go to our hydraulics page for this report and other information. And if you have any questions or anything, just let me or Matt know. Thank you very much.
Okay, thank you, Brian. And we have time for questions, of course. Joining Brian is Matt Lauffer, both of NCDOT. So we can open up with some questions. And again, feel free to post your questions during the presentation. We have one more presentation after this. So don't be afraid to go ahead and post your questions. One question we have up on the board is relative to the GIS data being publicly available. Is the GIS Surge Wave GIS database publicly available?
Yes, it is. It's just a large data set, so you just have to request it from us. And then we can usually get you the data that you need. You just, contact myself or just the hydraulics unit for DOT. The AGOL map is also out there. If you want to request a link for it, you can just ask us. We can get you set up with that information as also. The AGOL map just doesn't have as much information.
Okay, thank you. I have a question with regard to the data. Did you look at sea level change and introduce that, or do you have plans to introduce that?
When the report was written about 10 years ago, and at that time they didn't take that into consideration. I think that would be something that we would have to in the future. So it's just as it is right now. It's not part of that report.
Okay. Thank you. And I think the only other question that I might have is, again, it looks like there's significant coordination with your other departments there. So are you looking at expanding that, or especially the elements that are associated with just having the bridge watch? Is that being expanded to other bridges, or are you looking at just specific?
Actually, bridge watch is actually, we're piloting that right now within the state. And we actually have about 1,500 bridges, a little bit more. And part of those is about the 60 coastal ones. So we get alerts based on the surge models that come in, and that we're using the GIS data that was gathered during that report to help us, inform us and for those models. As far as expanding it, I'd also say that we're using, We have another program that we're spearheading, that there's actually a presentation tomorrow, D3 on, it's called Feynman T. So that would be a very, it's another just tool that we're using to help us use this data and make us more aware and make our roads safer.
All right, we have another question. What steps would you need to take before you get the surge wave GIS database up on the AGOL map? You mentioned you were interested in this.
I'm going to leave that one for Matt. We are working on it. It's a lot. It's a very large data set, and getting it onto the online platform is proving difficult, I guess. Not difficult. It's challenging.
Yeah, we're actually thinking about how to best present that data. So it's kind of complicated with all the TINs and information that's in there. So we're looking at like point and click, and then pulling the data for each of those locations and bringing up the actual data for that location. So we're working on it, but we were looking to have maybe like you click on it, you get the depth average current speed, the the current direction, the wind speed, water surface elevation, wave crest, and significant wave height, that type of thing, when you click on it in those locations. So yeah, that's been one of our challenges and one of the goals to get, and that's kind of why we're doing this presentation too, is just get some of the see what the interest is, so we can also kind of gauge that to see how many folks want to look at that. So
and I will say the AGOL database has all that, most of that information for the bridges themselves or the individual spans. What the GIS database that we have is, you can click and point anywhere on the map and get that information. We use that a lot for new bridge locations. And that's what's not shared, which we need to get out there.
Did you compare the surge wave data with the FEMA modeling results?
Yes. So North Carolina just redid their coastal surge analysis, and so we've been comparing that in different locations, and it's definitely more conservative, the level 3 wave analysis, than what's been currently published. So we take that into account when we're looking at our bridges and structures.
And I think we have time for one more question. Could you elaborate more? How does the output of SWAN and AdCirc model, I guess, how are the output of SWAN and AdCirc model used?
I'm going to have to say that, me and Matt, we're not coastal engineers. So typically we use the expertise of people like Brian and Ashley to help us answer questions like that. We're more interested in the results than how we can apply them. Okay.
Well, we might even have an opportunity to have that question answered a little bit later. But, well, Brian Radakovic and Matt Lauer, I really appreciate you coming on, both from the NCDOT and joining us today. Thank you very much. We're going to move on to our next presentation. This is the final one for this session, leveraging 2D storm surge modeling results to support graduate risk analysis. And this is with Ashley Kauppila of Taylor Engineering. So Ashley, take it away.
Hi, I'm Ashley Kauppila, and today I'm going to present leveraging 2D storm surge modeling results to support coastal graduated risk analyses. First, I'll go into a little bit about the background and motivation behind this work, which really focuses on calculating the wave height component of total flood depth or total water level associated with a coastal storm surge event. There are a few ways that we can do this, and the first one many of you are probably familiar with, as it contributes to the existing coastal flood insurance studies and your flood insurance rate map. And this method uses the WAFIS wave model to calculate wave heights and find total water level. And then we've also tried a few additional methods for finding total water level, including the 2D SWAN method and wave ratio method, which I'll go into. We'll look at total water level results compared between these three methods for a few different locations, for a few different frequencies, including the 0.2%, 1%, and 2% annual chance levels. And then we can look at the pros and cons of each method and draw our conclusions. So this work really evolved from the intent to shift from a binary depiction of flood risk, or what we traditionally think of as being in or out of the floodplain, and to a more graduated depiction of flood risk, where we're incorporating or considering a range of frequencies and also a range of coastal hazards. And while we attempt this, we want to leverage the existing data that we already have. Many of the coastal flood insurance studies over the last 10 years or so have amassed terabytes upon terabytes of data and thousands of model runs. And it would be nice to recycle that data to the greatest extent possible. And we also want to be able to calculate coastal flood risk at a structure-specific level. So for example, we'd like to, if someone is thinking about building a structure at a certain elevation, it would be nice to have a tool to quickly calculate the average annual loss that that structure would experience based on its localized depth damage function. So to give you a visual companion to the idea of shifting from binary to graduated depiction of flood risk, on the left, we have the binary version, which presents information similar to what you would see on your flood insurance rate map. And you can see discrete polygons delineating flood zones. And so in this depiction, the homes that are right on the beach would think, well, I'm in the V zone, I'm definitely going to flood. And then the homes a few blocks back in the gray that are outside of this special flood hazard area would think, I'm okay, I'm out of the floodplain. But we know that this is just a snapshot of risk at one specific frequency at the 1% annual chance level. And so the graduated version on the right considers a wider range of storm events, those that have a higher frequency but a lower severity, all the way to events that have a very low frequency and are extreme storms. And so we can see more of the wide range of risk on the right. So why make this change? Why switch to this graduated framework? Well, the existing flood mapping program really strive to provide a standardized suite of products, including that flood insurance rate map. And those products couldn't necessarily meet the diverse needs of coastal communities in assessing their flood risk. So this graduated framework will provide new types of data. For example, this mitigation hotspot map that you can see in the left panel here. It can provide new interpretations of existing data and shifting that mindset from thinking, am I in or out of the floodplain, to how can I reduce my risk? And finally, new uses for this data, such as a tool that homeowners might be able to use quickly to run a cost-benefit analysis on some type of flood-proofing measure that they're thinking about for their home. One important feature of this graduated risk framework is modular input data. So we want to be able to swap input data sets out quickly as new data becomes available. Coastal communities face risks through a variety of factors, which you can see here, including rising water levels, wave climate, land use changes, and the interaction between these factors is what defines their coastal flood risk and what defines the economics behind that risk. And these relationships are very dynamic. So when one thing changes, the whole flood risk profile shifts. And allowing for modular input will allow various stakeholders to see their updated risk quickly. Okay, so before I go into the modeling details, first I wanted to show a quick visual of the parameters involved in looking at coastal storm surge events. And we can think of a coastal flood as being some combination of the surge, which reaches the stillwater elevation, or that dashed horizontal red line, and some percentage of the wave height. So the wave height is on top of the swell, and the trough of the wave lies below the swell, and then some percentage of the wave and the wave crest is above the swell. And so the parameter that we're most interested in today is total water level. That's the vertical black line kind of towards the middle of this figure that includes the swell and the portion of the wave height that lies above the swell. So if we want to leverage existing data, first we have to look at what do we have? And for the existing coastal flood insurance studies on the Atlantic and Gulf Coast, at least, most, not all, but most of those studies have 2D hydrodynamic and wave modeling results for several hundred synthetic events. And this suite of synthetic events was intended to capture a wide range of frequencies for coastal flood representation. And more often than not, this particular model was 2D SWAN plus ADCIRC. And so the ADCIRC model calculates the hydrodynamics, the SWAN model calculates waves, and the two are tightly coupled, but this model was used to produce still water elevations or swell data. And so the SWAN wave height crests were not added onto the swell. So we have several hundred events that are giving us still water elevation data. And then the next step of the project included the WAFIS modeling. And so this is the transect-based, very detailed wave model that calculates wave heights for the 1% annual chance event. And so we combine the still water elevations and the WAFIS wave heights to get total water level at the 1% annual chance frequency, which we think of as the base flood elevation on our flood insurance rate maps. So what can we do with it? We know that we have still water elevation at a wide range of frequencies, but we only have wave height and total water level at the 1% level. And if we want to move to this graduated depiction of risk, then we need the wave heights and the total water levels at non-1% chance levels. So how can we do that? Well, a few ideas have been brought up over the years, and we tested them out for this. And the first idea is to scale the WAFIS results from the 1% annual chance event into other frequencies or other annual exceedance probabilities through what is called the wave ratio method, which assumes that the ratio of wave height to swell depth remains constant across the probability space. And then a second option that we wanted to try out was using the 2D SWAN plus ADCIRC results, or the SWAN component of that model directly as the wave crest. So first I'll go through a few details on how we calculate the total water level for these techniques. So first up, we have the one that many of you are familiar with, the WAFIS modeling and the flood insurance rate map technique, or what we'll call the firm total water level, where for the WAFIS model, we lay out 1D transects, which you can see an example of in this panel on the right. That's showing the transects laid out in Chatham County, Georgia. And so we use the swell data from the SWAN plus ADCIRC model as the initial conditions for the WAFIS model. We generate wind speed specific to a 1% annual chance event, and then combine the WAFIS and the swell and interpolate onto the 2D surface to get a two-dimensional total water level. For the 2D SWAN total water level, we started with our SWAN plus ADCIRC model results, and you can see on the right here an example of a SWAN plus ADCIRC mesh. This is the model topography for the Georgia and Northeast Florida SWAN plus ADCIRC mesh. And the nodal resolution along the shoreline in this mesh is approximately 80 meters. And so we have this mesh. It's not, the nodal spacing isn't as resolved as the WAFIS transects, but a big advantage of this model is that it's two-dimensional. So it can capture more of the nuance of what's going on with waves in the back bays. And our results here are also time varying. So we save out SWAN data that is tightly coupled with the ADCIRC model. So the physics of the two models are leapfrogging back and forth and informing each other throughout the model duration. And because we have the SWAN results for all of our several hundred synthetic events, we have this wave data available across the probability space. And we do maintain the WAFIS assumptions regarding the percentage of the wave height that lies above the swell, or 70% of the controlling wave height. And then finally, we have the wave ratio method. So this assumes that the ratio of wave height to stillwater depth that applies to the 1% annual exceedance probability also holds true across the probability space. So we need a lot of raster data to be able to do these calculations. We need the flood insurance rate map BFEs. So we need the total water levels that have already been calculated with WAFIS for the 1% annual chance event. And then we need rasters for every single stillwater elevation at every return period for which we want to calculate total water level. And then finally, we also need the raster of the topobathy DEM so that we can move between elevations and depths. And so with the wave ratio method, you can think of total water level as equaling the stillwater depth multiplied by some constant C, where C would range from 1 if there are no waves to 1.55 if we go all the way up to breaking waves. And the WAFIS modeling is really determining that C value depending on several factors: water depth, buildings, vegetation, and winds, of course. So we looked at these three methods for calculating total water level in Chatham County, Georgia, Duval County, Florida, and Sussex County, Delaware. And we wanted to focus our comparisons in two ways. We wanted to look at the firm total water level and compare that to the 2D SWAN total water level at the 1% annual chance level. And then we also wanted to compare the 2D SWAN total water level with the wave ratio method at non-1% annual chance levels. So we start by saying, how well do the 2D SWAN wave heights capture what WAFIS is representing? And then we can look at, well, how similar is the wave ratio method to the 2D SWAN total water level? So here are results for our three frequencies. First up, we have Chatham County, Georgia. And so we're going to start by looking at the results by subtracting the 2D SWAN total water level from the firm total water level. So we're looking at this contour plot to get an idea of the spatial variation in the difference between these two quantities. And so anywhere you see reds or warm colors is going to indicate that the firm total water level or the WAFIS total water level produce a higher flood depth or greater flood depth than the 2D SWAN version. And anywhere you see cool colors or blues is the opposite, where the 2D SWAN is producing the higher wave height. And so in the panel on the right, you can see all of Georgia, the results for all of Georgia, but it's hard to look at the detail here. That's a long stretch of coast. So then the panel on the left is showing zoomed into Chatham County. And we see a lot of warm colors in the marshes here. So generally we see that the firm total water level comes out a little bit higher than the 2D SWAN version. And the only region where we see a lot of dark red or a lot of really larger differences is in South Carolina on the north side of the Savannah River. So that's outside of the project area. Next, for the 1% annual chance level, we can compare firm total water level to 2D SWAN for Duval County, Florida. So this is the Jacksonville area. And once again, on the right, we have all of Northeast Florida, but it's really hard to see the detail of what's going on there. So then on the left, we've zoomed into Duval County. And in this instance, we can see, once again, warmer colors dominating, but we tend to see a string of nodes that are colored deeper red along the shoreline of the St. Johns River. So it's hard to say exactly why that's happening, but we do know that the WAFIS model or the firm total water level is coming out higher than the 2D SWAN in this instance. Another way to look at these results and to quantify them is to look at a histogram where we bin those total water level difference values into discrete segments, and then we can look at the distribution of those segments to figure out what's going on between the firm total water level versus the 2D SWAN. And for both Chatham County and Duval County at the 1% annual chance level, we can see that nearly half of the nodes produce differences in total water level that are within plus or minus half a foot of each other. So for a fairly large percentage of these nodes, the difference between the firm total water level and 2D SWAN is not that high. Then we can also see a few bins of 20 to 25% for both Chatham County and Duval County, with differences between a half foot to 2 feet. So we can see that the differences are skewed a little bit in the direction of the firm total water levels being higher than the 2D SWAN version. Next, we can look at the 0.2% annual chance or 0.2% annual exceedance probability for Chatham County. And we have the same, or instead of firm total water level, now we don't have that anymore for the 0.2%. So we're comparing the wave ratio method total water level and then subtracting 2D SWAN from that quantity. So anywhere that you see warm or red colors is going to indicate that the wave ratio method is providing higher total water levels than the 2D SWAN method. And vice versa for the cooler or blue levels are showing 2D SWAN coming out with a higher wave level or higher water level. And so in this case, we see the opposite trend and we tend to see more blues. So for the 0.2% annual chance event in this marshy area in Chatham County, 2D SWAN method is producing higher total water levels than the wave ratio method. And in this instance, only 30 to 35% of the results are matching within plus or minus half a foot. And if we compare 2D SWAN and wave ratio method at the 0.2% level for Duval County, we see that warmer colors are dominating, and we see quite a bit more dark red than we did at the 1% level with comparing the firm and the 2D SWAN total water level. So in this case, the wave ratio method is generally producing higher water levels than the 2D SWAN method, and about 35% of the nodes have total water levels that are falling within plus or minus half a foot of each other. At the 0.2% level, we can also look at Sussex County, Delaware. And so this is in southern Delaware, and we see warmer colors dominating again. So here also the wave ratio method is producing higher total water levels than the 2D SWAN method. And approximately 40% of the nodes are showing differences that lie within plus or minus half a foot. Then if we move to the 2% annual chance event, so an approximate 50-year return period, we can see that Chatham County generally is showing much lower differences between the 2D SWAN and wave ratio method when compared to the 0.2% annual chance, and that the differences are dominated by warmer colors or wave ratio method showing higher total water levels. And for this particular probability, we can see that 50% of the nodes are coming out within half a foot of each other. Then for Duval County, for the 2% annual chance event, once again, the magnitude of the differences seems to be quite a bit lower than at the 0.2% level. And we still see that the wave ratio method is producing higher total water levels than the 2D SWAN method. And 40% of the nodes are coming out within plus or minus half a foot. All right, and so what can we conclude from all of this information? So there are pluses and minuses to these two new methods of calculating total water level that we've tried out. The 2D SWAN method notably does not include erosion or any other structure-specific considerations. And the statistical analysis that we use for it doesn't include any uncertainty related to specifically to the incorporation of those swan waves. Whereas the wave ratio method does include erosion, but that erosion is sort of hardwired and tied to the 1% annual chance event, which of course is what was run for the original WAFIS calculations. And then the wave ratio method doesn't include any 2D physics in the waves. It's just a transect model that we then have to interpolate back onto the surface. Of course, an important consideration is what data do you have available? The data that we're focused on here is really specific to the Mid-Atlantic, Southern Atlantic, and Gulf coasts in the United States, but certainly there are other regions where some of the WAFIS data or the large suite of 2D SWAN data may not be available. And then we also need to make sure that we're considering that the storm suite for those 2D SWAN water levels must include the annual exceedance probability that you're trying to calculate total water level for. If that suite of storms doesn't include that frequency, then you're not going to be able to get very far. And so in conclusion, we know that FEMA is in the process of shifting over from a more binary depiction of flood risk, or thinking, am I in or am I out of that flood zone, to a graduated depiction of flood risk, where a range of frequencies and hazards is incorporated, and we can have this framework available to leverage the data that we already have to assess flood risk across that frequency space. And so in getting to this framework, we've tested out 2 different methods for calculating wave height and total water level associated with a particular storm surge event: the 2D SWAN total water level and the wave ratio method total water level, and generally found that the 2D SWAN results fell within 1 foot of the traditional flood insurance rate map total water levels at about 70% of model nodes within our area of interest. And we found that the wave ratio method total water levels typically fell within 1 foot of the 2D SWAN version at 50 to 60% of the model mesh nodes in the area of interest. So that's all I have, and I'd be happy to take questions. Thank you.
Thank you. Thank you, Ashley, for that presentation. We have Ashley with us to answer questions. If you have any questions, please type them in now. And we have a time for a few questions, I'd say. First one up, Ashley, as you mentioned, wanting to enable modular inputs, which of these methods that you discussed may be more suitable for a modular framework?
Well, I would say that scaling the WAFIS results may be more suitable for a modular framework because, like I said, all of the data that goes into that already exists typically in raster format. So it's a lot of data, but it's already out there. And so I think probably scaling the WAFIS results.
Okay.
Data, you need to, sometimes that's in different formats, and it can be a little bit more difficult to work with.
All right, next question. Is there any way to test a model other than a real storm? Do you have feedback from an event for an area model to see if it matched the outputs? And can one run a known storm over the model to test the projections?
I'm sorry, can you say that?
So is there any way to test a model other than a real storm? But I think the other part of it, maybe do you have feedback from an event or an area model to see if it matches the output? I guess it's more of a verification test they're talking about.
Good question. So all of this work was done using the synthetic storm suite. And no, we have not been able to go back and look at the previous validation runs for these 2 studies, for the Georgia Northeast Florida study and the Region 3 study in Delaware. We haven't been able to go back and look at the validation storms and see how they shook out in terms of return period and how we did with the waves there. So that would be an interesting direction to take it in the future, to check these two methods.
And I guess the second part, and forgive me if I missed it in your answer there, can one run a known storm over the model to test the projection? Or you may have answered that in your answer, I don't know.
I think so. I think that that question is asking about doing this with a validation storm from one of these studies and checking how our two methods did against that validation storm. Okay,
sorry about that. All right, and question you mentioned there, I might have missed it. The frequency range you mentioned. Can you elaborate on that?
Sure. So the 2D SWAN plus AdCirc model was run for several hundred storms that were designed to simulate a range of frequencies, but typically not the highest frequency events. So the actual cutoffs depend on the study, and it varies from region to region. But quite a few of the studies used tide gauge analysis for the high frequency events. And generally speaking, the synthetic storm suites would cover from about a 50-year return period to 500-year return period. Okay.
And then I asked this question before, but I'll dare do it again. Was sea level rise considered in there, or is there future consideration for it? Understanding this might have started before sea level rise was being considered.
So sea level rise was not considered as part of this sort of pilot study. So this work was based off of products that go into the flood insurance rate maps that are really a regulatory product. And those are developed based on present day conditions because people are determining their flood risk right now for these regulatory products and not so much in the future. But that's another variable that would make these results interesting. Another interesting thing you could look into.
Right, and it brings up a question that may go more toward policy is what is the impact of the proposed gradual coastal risk on insurance rates? I think that might be in another forum, perhaps. It's a good question and one that's in the back of my mind too, with risk rating 2.0 coming out. But I think you and I were just talking offline about this process being very aligned with this risk rating 2.0 graduated risk analysis.
Yeah, it is aligned. I can't say for sure yet exactly how it could impact things. This is sort of hot off the presses, but this is all part of that strategy to move away from just harping on that 1% annual chance.
Yeah, no, it's a real good program, a real good idea moving in that direction. I'm happy that you're looking at these things, and really appreciate Ashley Kauppila of Taylor Engineering being with us today. Thank you very much for your presentation, and thank you all of you in the graduated time zones for being here to listen to our session B3. We're wrapping up right now, and you're encouraged to get ready to join the next session at 3:30 p.m. That's Central Time. So again, thank you everyone for joining us.